Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about z-test. I hope the screen is visible. So this is a very important statistical test for normally distributed data. So let's set up the agenda. So we'll discuss about z-test. Within that, we'll understand what is z-score. Then we'll do a quick revision of standard error. I have discussed about standard error at length in my CLT or central limit theorem video. Okay, I'll put a link of that video in the description. And then we'll discuss about one sample z-test and two sample z-test. And this one sample or two sample, both of them, when we say, we mean it is a mean test. Okay, let's go one by one. So let's start. What is z-test? So z-test is a parametric test. So all these are the types of hypothesis test. Okay, these are the tests which are used as a part of hypothesis testing. So we covered student's t-test, and this is a z-test for normal distributed data. So this is a parametric test. Parametric statistical test means it makes some assumption about the underlying data. It says that the population variance is known and the data is normally distributed. So that's what we mean when we say that that's a parametric statistical test. Means that it makes some assumption on the distribution of the underlying data and the parameters that are there. So it assumes that the population variance or population standard deviation is known. Okay, in t-test the population standard deviation was unknown because the sample size was less than 30 or a small sample. This is known, and then sample size is large. We say typically n is greater than or equal to 30. Okay, and this is used to, so these are all for comparing means. So there are two types of tests, one sample and two sample. In one sample z-test, we compare the sample mean to the population mean or some known value, and in two sample mean z-test, we'll compare the means of two independent groups or two independent samples. That's what it is. Okay, so let's understand. So this is z-test. So this z-test is assuming that the underlying data is normally distributed. Okay, so for this, we know that in if the data is normally distributed, right? If the data is normally distributed, this is mu is 0. If it is n 0 1, that is mu is 0. Mu is equal to 0 and variance is 1, that is standardized. Then we know that anyways, even if it's not standardized, if it's not 0, even then it holds that within one standard deviation, this is minus 1 sigma, this is plus 1 sigma. So within this range 68% of your data lies. And similarly within 2 standard deviation, minus 2 sigma until this is minus 2 sigma, and here this is plus 2 sigma till here, then 95% of data lies here, and till 3 sigma 99%. Okay, we know that already. So we know that for normally distributed data, that 68% of data, okay, 8% of data lies within plus minus 1 standard deviation. 95, this is 95.4. I'll write 95% of data lies within plus minus 2 standard deviation, and 99% of data lies within plus minus 3 standard deviation, and so on. So we know this because that is normally distributed. And for capturing this, we have something called, okay, for all this. So this is 1 standard deviation, 2 standard deviation, like this, right? So these values, okay, so we'll have all the values in between also. So there'll be value, this value will vary from 0 to 100, this percentage, and there will be corresponding value for the standard deviation. Okay, and these corresponding values, these are known as z-score or z-score. Z or Z, I use them interchangeably. Okay, this is a standard score to measure the standard deviation after the data is normalized. or sorry, data is standardized. Standardized means, so this is z-score for measuring the standard deviation of specific data point, of a specific data point. So each data point, so they had all these data points are here. So this is a data point here, right? For each data point, if I know that it is +1 standard deviation, then this will be like 34% of area will be there. If this is the data point is there, how far it is from the mean. Okay, if we know that, then we can find out. So if this, okay, so for example, if I have another standard, if I have another distribution whose mean, okay, whose mu, okay, is not, okay, so let me draw. I'll explain what standardization means. Okay, so there are, say, two distributions, and the mean for this is, say, for example, this is 0 and this is 5. Okay, so it's on the number line itself. So but the distribution, say, everything is identical, the variance is same, the sigma for them is same. So, or even if the sigma is different, if this is fatter and this is thinner, so what we can do is we can convert any other normal distribution, we can center the mean to 0, so that the calculations, it becomes standardized, all the data for, so then we can compare any kind of data set. Okay, after standardizing it. Standardizing means mean centered and variance scaled, variance is for the sigma, and generally variance, instead of variance we use the standard deviation for scaling, because the data or the units of the data point and the standard deviation, they are the same, because standard deviation is square root of variance. Okay, so for, if we write the formula, how do we write it? So z score, so that is a standardized score. So that's what I was trying to explain you. Z score is for each data point. For each data point we standardize it, we bring its mean to 0. So if we subtract the mean here, this is the difference between the mean of these two. If I subtract, this is the new mean. If I subtract the mean of this data point, wherever, say if this is going till here, so this data points will shift by 5 here. If this was here, will come here. So the mean of, if this was the mean here, it will shift to this 0 mean. Sorry, that's what I mean. And even for these, all these data sets, right? So they will, if I subtract for all of these data points, they will shift, this complete thing will shift here, and this will become a bell shaped curved, which is centered on around 0 instead of being centered around around 5. All these data points, if I subtract 5 5 5 5 5 from this, they will all shift here, -5 -5, they will all shift this side, right? That's what I mean by mean centered. And variance scales, if the variance is whatever is the variance, right? I can, if I divide by them, and here the variance is 1. Here if I say the sigma is equal to 1. So say for example, if the sigma here, this is more thick, sigma here is equal to 2. If I divide by the variance, the standard deviation, that's what I mean. Okay, I use them. Okay, that is square root of variance. If I divide by 2, then my standard deviation will also become 1. Whatever is the standard deviation of these points, of all these data points, whatever I'm getting, if I divide by the standard deviation of this distribution, then it will become 1. And that's what I want, that the mean should be 0 and the variance should be 1. So mean centered and variance scaled. So I subtract the mean and divide by the standard deviation for each data point. So now this distribution will become this distribution, and the data points will adjust accordingly. I hope this is clear now. So this is simple maths, I just want to explain that. So this will become, for each data point, x minus mu by sigma. Mu is your population mean, and this is your population standard deviation, and this is your data point. So if I know that, so for that data point, after I have standardized for, and then I can use the z-score, that what will be the z-score if sigma is 1, because I know that ±1 sigma, 2 sigma. So now the units are standardized, it is 1 2 3, and now it's easier to compute or calculate. So if my data point is here, I can check whether how many standard deviations far it is from here, and what will be the area if I want to see the area of the curve under this. So I can just compute the area of the curve under this. This whole area will be there to the left of this data point. So there are other ways I can calculate for the left, for the right, depending upon that. But most common is left of the data point. What is the area under this curve? And since this is a PDF, you know that area under the curve of any PDF is 1. And in percentile terms, it is 100%. And that's what I mean. So the data lies within this means the area under the curve will be 68% within one standard deviation. I hope this is clear now. Okay, let's move. So this X is individual data point. Okay, so Z-score helps define the probabilities. So these are the standard probabilities this of finding the data plus this standard deviation, the mapping. This Z-score maps these two values. Okay, so compares. So this is your and there difference between means. Okay, and difference between the this is difference between the data point and the mean, population mean divided by the standard deviation. I hope Z-score is clear. We will come again when we solve a problem, right? We'll again refer a Z-score table similar to what we saw in the student sheet distribution. We'll again refer a table. This will have all these values and we can check out. Here also you can see clearly, say for example, whatever is this value is 1, for example, this will be standard deviation 1, right? And here -1. So there will be plus 34% data here and minus 34%, plus 34, like that. So the value will be 34, right? This is -1. This will be +1. So the data, the percentage of area within this would be 34 plus 34 68. And if I take the complete thing, then this is 34 here, this is 50 here, 50 plus 3, 84% at +1 standard deviation, right? If everything, I take everything to the left of this. So this is 34 after 0 and 50 remaining, because this is symmetric. This is symmetric curve. So that's how it is. So I can calculate, just map the standard deviation, how many standard deviations away that data point is from the mean after standardizing, and I can just get the location, how much area under the curve comes under this. Okay, a side mean or total area. That's your Z-score. Now using this Z-score, we do the Z-test. Now let's move to the Z-test. When we see the Z table, it will become more clear. Okay, Z-score table, it will become more clear. But I hope this makes sense. Okay. So let's Z-test. It is just simple stuff. So I'll talk about 2 Z-tests. Okay. So it is to test if sample mean is significantly different from a known population mean. So this is your one sample Z-test. One sample mean is implicit. So this is all for comparing means only. So this is to compare sample mean to population mean. Sample mean is your X bar and this is your mu. That's what it compares. And for all the tests, there will be a test statistic. So what is the test statistic for this? So this is called Z. Like for T distribution, it was T, right? So this is called Z. Okay, and this is equal to. So as I told earlier, the numerator will always be a difference of the means when it is a mean test, and the denominator will be some form of standard deviation. Here it is sigma by root n. Okay, so this is your sample mean. We know this. This is your population mean or a known mean, some true value. Okay. This is sometimes 0, may not also. This is your sample size, and this is your known population standard deviation. Population standard deviation. And this denominator term, if you check my central limit theorem video, we have discussed a lot about this. That's what I was mentioning at the start of the video. This sigma by root n, this has also got another name, that is, it is called standard error. Standard error. Okay, what is standard error? We have discussed there. I'll just give you a brief about it. So this Z statistic, so it will follow some distribution. So it follows a normal distribution. That's where the Z score comes from. Okay, so this Z statistic will follow follow a normal distribution. We'll write that also. So the distribution, underlying distribution is normal or Gaussian distribution. that bell shape, standard bell shaped curve. Okay, and standard error, what we mean here, this is a standard error. Okay, so this, whatever is the population standard deviation, this is divided by square root of the sample size. This is called standard error because this gives us the standard deviation of sample means. Okay, this is a standard error. If you remember central limit theorem, when we took multiple samples and we did we have samples, right? So we have samples x1 to xn, trial 1, trial 2, x1 to xn. Like this we did k trials, x1 to xn, and then we had x1 bar, we had x2 bar, like this we had xk bar. Okay, so we have this n sample means, sorry, remember from the central limit theorem. So we have this n sample means, and when we plot this sample means, this will follow a Gaussian distribution with mean mu, and same, it will converge to the population mean, and the variance will be sigma square by n, and the square root of this was the standard deviation of the, and this sample means follow a Gaussian distribution, and this is the variance of that, and the square root of that is the standard deviation of the sample means. Okay, and you have done the derivation also for this. Check that, I'll put the link in the description. So this is what it means. It is the standard deviation of the sample means, and the standard deviation of the data of the population data is sigma, but for the means this is sigma by root n, and that is called standard error. I hope standard error is clear and it's revised again. Okay, and what is two sample z test? So this is a test statistic, simple here. Similarly, what is a two sample z test? So we have, in one we are comparing just sample mean to population mean. Similarly, when we compare two independent samples, we have two groups and we want to compare the means of the two groups, then we use two sample mean test. So we write two sample, I'll skip the mean, two sample z test. Okay, so this is used to compare means of two independent samples or two independent groups. So I'll just write it, compare means of two independent samples. Okay, and the statistic associated with this would be, this is two sample, so what will be the test statistic? Again, the difference of the two sample means x1 bar minus x2 bar divided by standard deviation in some form. Okay, so this will be a sigma square by n1 plus sigma 2 square by n2. Okay, the square root is this, so this is your, these are your sample means, and then we standardize it by, so if you take square root of, these are variances, right? These are population variance which is known for both the samples. When we scale it, we divide it by n1 and n2 so that it's standardized, and then finally we divide it. So this whole term will be acting as sigma or standard deviation, and the units of both will be same, and that's how we standardize the test statistic. So as I mentioned earlier, all the test statistic will be some form of mean. If it is comparing means, it will be mean by some form of standard deviation. We have seen this in t-test also. Okay, so if this is there, if this is understood, okay, simple. Now let's do a quick problem to understand it. This z-test is very simple. Okay, the only thing is tricky part is many people don't understand how to check the z-score table. I'll show you that quickly, but let's do a problem now. So we have the known population mean of the ML model is 1/22. Okay, I won't make it one more. So your mu naught is, this is your known population mean or the existing runtime of ML model. The existing runtime is 120 seconds. Okay, and after the new optimization, a new optimization was applied. So new optimization is applied, and now this changed to 117 seconds. Okay, and the sample size for one sample only. So the sample size is how many samples we took? That was 100. So n is 100 here. Okay, 100 runs. We did 100 runs and we found out that the new runtime was 117 seconds for that model after the optimization was applied. Now, does the optimization have a significant impact on the to reduce the runtime or not? We need to validate this claim. So, did the optimization have the impact? Did the new optimization? So this is a hypothesis testing. Did the new optimization have significant impact to reduce the runtime? Okay, so that's the question, and we will see. We'll put the alpha or significance level as 5%. This is your significance level. So we'll follow the standard template of hypothesis testing. We'll go one by one, and so that it becomes very clear to you. And if you have not seen the hypothesis testing video, please go and check that. That has all the details. How to do, what does all the term mean. So we start with what is the very first step for any hypothesis testing. We start with the what is the null hypothesis and what is the alternate hypothesis. We first of all fix this. So my first alternate the null hypothesis is that nothing has changed. Always it maintains the status quo, means your runtime has not improved, it is same. So your mu still remains 120 seconds, no change. Okay, and my alternate hypothesis is that it has reduced, right? So we have found that this is 117 seconds. So my alternate hypothesis is that whether it has reduced significantly due to the new optimization or not. So my alternate hypothesis will be that it is less than 120 seconds, whether it has reduced or not after the optimization. This is the claim we need to validate, and we have this 100 samples or 100 runs. We did 100 runs and we got some data, and the mean of that data was 117. And using the z-test, one-sided z-test, will confirm this. Okay, so what is my test statistic for one-sided z-test? So because we are just comparing from the sample mean, we are ascertaining the population mean. So my test statistic is z, this is equal to x bar, and what is my x bar here? Sample mean after 100 runs is equal to 117 seconds, and n is equal to 100 runs. 100 times I have run current time. So this is what it is, minus mu by my standard error, sigma by root n. What is sigma? Sigma was given, okay, population standard deviation. Okay, we missed it in the problem, so let's write that. So sigma is let me write down here. So the known population standard deviation, no optimization. Okay, sample size is this, and population standard deviation is equal to say 15. This is your sigma. Okay, so this is your standard deviation. 15, 100, 117 seconds, 120 second was the population mean. This is your x bar, this is your sigma, this is your n. All the parameters are here now. Now let's just put it in and check with the z-score. So this is a null hypothesis that nothing has changed. The runtime is still 120 seconds. Alternate hypothesis is no. After the new optimization, it had an impact and it reduced the runtime below 120 seconds. Okay, now let's compute it quickly. So what is z statistic equal to? 117 minus 120 by sigma is 15 by square root of 100 is equal to minus 3 by 15 by 10. 5 3s are, okay, 5 3s are, and this is 5 2s are. Okay. So this 3 and 3 goes off, and then this will come out to minus 2. So my z statistic, okay, observed is equal to minus 2. And what was my significance level? 5%. Okay, so this is one-sided because we are comparing less than. So less than is left side. This is coming as negative, so my mean is less than. If it would be greater than, I'll go to the right sided test, and if it is less than, then we'll go to the left sided one tail test. So if you don't understand this, check my hypothesis testing video. What is one-sided tail test or two-sided tail test? So for example, this is my mean here, whatever is the mu. Okay, if it is less, okay, here this x bar is less than this. This is what we are doing, that x bar is less than mu. This is my alternate hypothesis. X bar is less than mu. That's what we are saying, that this is x bar. That's what we want to ascertain. So this net value, anyways, it has, we have got -2. So this will come to the left side of the, because the value will be negative. This net value, because the bottom, this is always going to be positive. So numerator will decide whether I go left or right. If this would have been positive, if I was saying that x bar is greater than 120, then I'll go towards the right, because the values that I will get in the observation of the test statistic would be positive. And since it's negative, we'll go towards the left side. So we have found out that this is somewhere around -2, right? So this is -2. So and what is our alpha? Alpha is 5%. So that is 0.05. Now let's check the z table. Okay, so this is so the p value here, so there will be p value. So we have done steps. We found out what is our null and alternate hypothesis. We fixed that. We computed our test statistic. We saw its distribution. Then we found out what is our alpha. Then we'll calculate our p value. So the p value would be area under the curve here. This will be my p value. On this side, to the left of this. And now we have to find out the significance value is there. So now what is t alpha? This is the critical value. So this is your critical value, for which my area under the curve will be less than 5%. Okay, less than 5%, and 5% will be 0.05. So let's see the z-score table. So if you see here, I've opened the table. If you just go and Google z-score table PDF, you will get the table. Okay, I have opened one table. So here, if you see, there are important hypothesis testing critical values. It's written already. So if the significance level is 0.05, if you see here 0.05, what is the corresponding value for the left tail test? -1.645. We'll just take it from here itself. So my critical value here will be equal to -1.645. So this is your, here mu is 0, right? Because this is centered, mean centered variance scale. 0 is 0. For z-score also, everything is centered as 0. N 0, 1. So and this is -2.0, whatever. And this thing comes out to be, the t alpha comes out to be, this is t alpha, and this is equal to 1.645. And my critical value is this. So my area under the curve to the left of this will be 5%. This is my significance level. But if you see, my t observed or z observed is towards the left, so the area under this curve would be definitely less than 5%. Means, what does this say? That p value is less than alpha, or 5%. So this is less than the significance level. So what do? We reject null hypothesis and accept alternate hypothesis. And what is our alternate hypothesis? That there is a significant evidence that the runtime, okay, is below 120 seconds. It has, this new optimization has improved the runtime, and it is below 120 seconds. That was our alternate hypothesis. Where was alternate hypothesis? Yeah, here. So we accept this. Yeah, due to the new optimization, my runtime has significantly reduced, and it is now below 120 seconds. We accept this alternate hypothesis because we rejected our null hypothesis. Okay, so I hope this is clear, simple. So I knowingly took a left tail test because I have been taking right tail test earlier in t-tests. So I will be taking all kinds of tests so that you get a clear understanding of all the kinds of options or the combinations that can happen in hypothesis testing. I hope this is clear. Okay, let's do a quick revision. So we understood what is z-test, very simple, very common. Okay, so this is a parametric statistical test because it assumes the distribution of the underlying data, that it should be normal, plus the parameter of this population standard deviation is known. So that's why it's a parametric standard test, and this is valid for um, large data set where n is sample size is greater than or equal to 30, at least 30, and population standard deviation is known. Okay, and then we saw that within plus minus 1 standard deviation we have 68% of data for a normal distribution, 95% of data within 2 standard deviation, and 99% of data within 3 plus minus 3 standard deviation. We saw that, and then we saw z-score, that is a standardized score for each data point. And we saw how do we standardize the score. For each data point we subtract the mean and divide it by the standard deviation. That's how we standardize it. We bring it towards 0. So if we subtract this will minus 5, so this will come to 0, and we'll divide it by the standard deviation. So that's how we standardize, and this z-score gives the mapping between standard deviation and the percentage of area under the normal distribution. So this mapping gives me this, okay, on both the sets. And then using this z-score, okay, we do the z-test. And there are two types, one sample z-test and two sample z-test. One sample z-test compares the sample mean to the known population mean, and the test statistics is given by x bar, that is mean minus mu population mean, or the known value, some known value, hypothesized value. We compare that and divide it by sigma by square root of 9. And this sigma by square root of n, standard deviation by square root of n, this has got a name standard error, which comes from our central limit theorem. Watch that video. I have discussed in this video also, and that should be sufficient to make you understand. And then we discussed about two sample z-test, where we compare means of two independent samples or two groups which are independent. And then we did we saw the test statistic where we are comparing the means of the two groups, and then the denominator has a sigma 1 square by n1 plus sigma 2 square by n1. This is a variance square, and then we took a square root, which is kind of form of variance which is scaled. Okay, so this is your test statistic which we measure. And then we saw a simple problem for one-sided z-test, where we compared the improvement in the runtime of a model which earlier had 120-second runtime, and then after some improvement with new optimizations, we claim that the runtime has reduced below 120 seconds. And then we did 100 runs, and we found out the sample mean of that was 117 seconds. And the standard deviation of that population was known as 15. We used all this data to compute the z-score, z statistic, or the test statistic. Okay, and from there, this was the z observed. This is your test statistic. And then we found out this is -2, and this is a left tail test because x we are trying to find whether my sample mean is less than the some known value or the population mean. So whenever this is less, so we'll go towards the left side, and if it is a greater, then we'll go towards the right tail test. So we saw the left tail test, and finally we saw that the area under the curve is less than the significance level because -2 is less than 1.645. So the net area, the p-value, the area under the curve will be less than the significance level. So we reject the null hypothesis here and accept the alternate hypothesis, which is that yes, the runtime has significantly reduced due to the new optimization. I hope this is clear. Thanks for watching this video. Have a great day, and bye for now.